Imagine you are 45 minutes into a grueling technical interview. Your palms are sweating. The interviewer looks across the screen and asks, how do you ensure data consistency in a distributed system? What you say in the next 60 seconds could determine a massive job offer. Welcome in, everyone. Today, we are running a realistic simulation of a Micro1 software engineer interview. Just to be absolutely clear up front, this is a practice scenario that we built. It is inspired by publicly available information and real candidate experiences, and our mission today is to help you prepare by extracting the most important technical insights from all those sources. I will be playing the role of the interviewer, and my co-host will be your candidate. We are going to stay in character for almost the entire simulation. After each response, I will briefly step out of character to offer just a couple sentences of concise coaching before we immediately jump right back in. Let us begin. Are you ready?
Yeah, I am ready when you are.
Hello and welcome. To start things off today, tell me about yourself.
Thank you. I'm a software engineer with a strong background in building and, scaling web applications. Over my career, I have had the opportunity to work across the stack, which has given me a pretty comprehensive understanding of how different system components interact with each other. On the back end, my primary focus has been working with Node.js to design and implement RESTful APIs. I really enjoy the architectural challenges of back-end development, particularly optimizing for data flow and ensuring secure, efficient endpoints. And on the front end, I specialize in React. I have spent a lot of time building dynamic responsive user interfaces and managing complex state across the componentry. Ultimately, my goal is always to deliver clean, maintainable code that directly supports the broader objectives of the project and, provides a seamless experience for the end user.
Just to pause you right there, when you say you optimize for data flow on the back end, can you give me a sense of the scale you are typically working with?
Absolutely. So in my most recent role, we were processing roughly 2 million active requests per day. The optimization challenge there was not just about making a single query fast, but ensuring the entire pipeline could handle concurrent data streams without choking the main database thread. That basically meant heavily relying on asynchronous processing and strategic caching to keep latency under 50 milliseconds on our core endpoints.
Stepping out of character for a brief evaluation. Strong answer. You clearly explained your background and set up your core technical competencies without rambling, and smoothly handled the interruption to provide concrete scale. All right, back into the interview. How do you manage to get the work done when you are under pressure? Tell me about a time you handled a situation like that.
Pressure is definitely a constant in software engineering, and I find that the best way to handle it is through strict prioritization and breaking large problems down into manageable steps. A specific situation that comes to mind was during a recent product launch. We were on a very tight deadline, and right before the target date, I was tasked with handling a massive influx of messy, unstructured data. We had thousands of CSV files with mismatched date formats and missing fields that needed to be integrated into our system before the launch could even proceed. The situation was high stakes because failing to process this data would delay the entire release.
Right, so how did you tackle that?
Well, my task was to clean, validate, and pre-process this data quickly without compromising the integrity of our primary database. The first action I took was to isolate the data. I wrote a series of pre-processing scripts using regular expressions to standardize the date formats, and I applied safe logical defaults for any missing values so the pipeline would not just completely break. And most importantly, I chunked the data processing into smaller batches.
I want to dig into that point right there. Why chunk the data instead of just running a single bulk insert? Was that a time constraint issue?
It was actually a memory and stability issue. If you try to load gigabytes of unstructured data into memory all at once, you risk overwhelming the Node.js process and causing a total crash. By chunking the data into smaller, discrete batches, I ensured our memory footprint stayed flat. It also meant that if one specific batch contained a critical formatting error, only that small batch would fail. We could monitor for errors in real time, catch the bad batch, fix the logic, and keep the rest of the pipeline moving. The result of this methodical approach was that we successfully pre-processed the entire data set, 0 critical errors were introduced into the main database, and we successfully hit our deployment target exactly on schedule.
Evaluation, no, excellent structure. You implicitly use the situation, task, action, result framework, and you successfully defended your technical reasoning when pressed on the mechanism of your solution. Resuming the interview, You mentioned dealing with heavy data workloads just now. What are the strategies you use to design RESTful APIs that efficiently handle heavy data traffic?
Designing RESTful APIs for heavy traffic really requires a multi-layered approach to ensure the server does not get overwhelmed and the client receives responses quickly. The first strategy I always look at is limiting the payload size. I implement pagination on endpoints that return lists of data. This ensures the client only requests and receives the specific chunk of data they need at that exact moment instead of everything at once.
Let me stop you right there. When you say pagination, are you talking about offset-based pagination or cursor-based pagination?
Oh, for heavy data traffic, I strongly prefer cursor-based pagination. Offset pagination gets incredibly slow as the dataset grows because the database still has to count and skip all the previous rows just to get to your requested offset. Cursor-based pagination uses a unique identifier, like a timestamp or an ID, as a pointer. The database just jumps straight to that index, which makes the query execution time essentially constant no matter how deep into the data the user scrolls.
Got it. What else besides pagination?
Beyond pagination, another critical strategy is caching. If there are frequent responses that do not change constantly, I will implement a caching layer using something like Redis. This prevents the API from having to query the primary database for every single request, which drastically reduces latency. And additionally, to protect the system from sudden traffic spikes, I apply rate limiting at the API gateway level.
Strong points. But I do have to push back on caching. Caching can lead to stale data. As an interviewer, if a candidate mentions caching, I immediately want to know how you handle cache invalidation. How do you ensure users are not seeing outdated information?
That is a very critical point. Stale data can completely ruin the user experience. My primary mechanism for handling this is setting time to live, or TTL, headers. You can think of TTL like an expiration date on a carton of milk. I set a specific time limit, say 60 seconds, where the data is considered fresh. Once the clock runs out, the cache throws the old data away, and the next request forces the system to fetch the fresh data directly from the primary database. If the data is highly sensitive and even 60 seconds is just too long, I will use event-driven invalidation, where any write operation to the database automatically triggers a script to instantly purge the related cache.
And what about the rate limiting you mentioned earlier? How exactly does that protect the server?
Rate limiting acts exactly like a bouncer at a crowded nightclub. The bouncer only lets a certain number of people through the door per minute. If too many people try to rush in all at once, the floor might collapse. In an API context, rate limiting restricts how many requests a single IP address or user account can make within a given time window. If they exceed that limit, the server simply returns a 42920, too many requests status code, and refuses to process it. This ensures that no single user, whether malicious or just running a poorly written script, can consume all the server's CPU and memory resources.
Evaluation note. Phenomenal detail. You defended your architectural choices perfectly and used clear analogies to explain complex mechanisms, which proves true mastery of the subject. Resuming the interview, let us push a bit deeper into backend architecture. How do you ensure data consistency and integrity in distributed database systems?
Ensuring consistency and integrity in a distributed system is definitely one of the more complex challenges in back-end engineering. The approach really depends on the specific requirements of the application. If strict consistency is absolutely required, like in a financial transaction transferring money between two accounts, I would leverage distributed transactions and adhere to strict ACID principles. This guarantees that all parts of the transaction succeed or fail together. However, in many distributed systems, strict ACID compliance creates massive performance bottlenecks. In those cases, I lean toward BASE principles, which stands for basically available, soft state, and eventual consistency.
You just noted that strict ACID compliance creates massive performance bottlenecks. Why exactly does that happen? Walk me through the mechanism.
It really comes down to database locking. To guarantee that data is perfectly consistent across a distributed system in real time, the system has to lock the records being modified. You can think of it like a rare reference book in a library. If one person is reading it, no one else is allowed to touch it, read it, or write in it until the first person completely finishes and returns it to the shelf. In a distributed database, if node A is updating a record, nodes B, C, and D must wait in a queue for the lock to be released before they can process their own transactions. And at a massive scale, that queuing creates severe latency.
Right. So if you move away from ACID to avoid that locking and you lean into base principles, how do you handle consensus? For instance, how would you apply algorithms like Paxos or Raft?
I will admit I do not recall the exact granular mechanics of consensus algorithms like Paxos or Raft off the top of my head right now. But I do understand their underlying purpose is to ensure that a cluster of distributed nodes can agree on a single source of truth, even if some nodes drop offline or fail. Instead of relying on strict locking mechanisms, my logical approach for most applications is designing for eventual consistency using message queues like RabbitMQ or Kafka.
How does that work in practice?
It works a lot like the Postal Service. When a user updates their profile, the system does not wait to instantly update every database node simultaneously. Instead, it drops an update message into a queue. The other microservices pick up that message and process it asynchronously when they have the resources available. To maintain data integrity in this model, it is crucial to implement continuous monitoring and design your operations to be idempotent, meaning if the same message is accidentally processed twice, it will not corrupt the final state of the data.
Evaluation note. Perfect recovery. Admitting a specific knowledge gap while explaining your reasoning is infinitely better than guessing. Plus, explaining the underlying mechanism of database locking was a great touch. Resuming the interview. Let us shift our focus and talk about the front end. Since you work heavily with React, what are the differences between use memo and use context, and when would you use them?
They are both very useful React hooks, but they serve entirely different purposes. UseMemo is a performance optimization tool. It is used to cache or memoize the actual result of a calculation between renders. The way it works under the hood is that React stores the result in memory along with a dependency array. I would use UseMemo when I have a computationally expensive function, like filtering or sorting a massive array of user data, and I only want that function to rerun when its specific dependencies change, rather than on every single render of the component. On the other hand, useContext is used for passing data through the component tree without having to manually pass props down through every single level.
Prop drilling, right. Can you explain why prop drilling is something we want to avoid?
Exactly, prop drilling. It is a lot like playing a game of telephone down a line of 50 people. If the component at the very top of the tree needs to send data to a component at the very bottom, you have to pass that data through every single intermediate component, even if those middle components do not care about the data at all. It clutters the code and makes it a total nightmare to maintain. UseContext solves this by acting like a global PA system for your application. You broadcast the data at the top level using a provider, and any component anywhere in the building can tune in and listen to that data directly using the UseContext hook. I use it for global data that many different components need access to, such as the current authenticated user, the UI theme, or shared application state.
You mentioned state just now. What exactly is state, and how is it beneficial in React apps?
State is essentially a built-in React object that is used to store data or property values that belong to a specific component. You can think of it as a component's short-term memory. The primary benefit of state is that it enables dynamic and interactive applications. When the state object changes, say a user types a letter into a search bar, React notices that the memory has changed. It then uses its virtual DOM diffing algorithm to compare the new state to the old state, and it automatically triggers a re-render of just that specific component to reflect those changes in the user interface. Without state, a component would be entirely static, only able to render what is hard-coded or passed to it via props.
Evaluation note. You handled the interruption and pivot smoothly. Using the PA system analogy made your explanation of loose context incredibly vivid and memorable. Resuming the interview. Let us move to a situational question. How would you investigate a web app that is performing slowly?
Troubleshooting a slow web app requires isolating the bottleneck. So I would take a systematic approach, moving from the client side all the way back to the server. First, I would open the browser's developer tools and look at the network tab. I want to see if the slow performance is caused by massive payload sizes, slow API responses, or too many network requests blocking each other from firing.
What if the network tab shows that the API responses are blazing fast, but the user still reports massive lag on the screen?
Well, if the network requests are fast, the issue is almost certainly on the front-end execution. I would use React's profiling tools and Chrome's Lighthouse feature to analyze the render cycles. I'm specifically looking for unoptimized components that are re-rendering unnecessarily, or heavy synchronous JavaScript operations that are blocking the main thread, which freezes the browser's ability to paint the pixels on the screen.
Let us flip the scenario. What if the network tab shows that the API itself is agonizingly slow to respond or returning explicit errors?
Then I need to investigate the backend environment. I would start by checking the database performance monitoring tools, looking for slow queries, missing indexes, or maybe a saturated connection pool. If the database is healthy, I would check the server logs directly. I want to see if the Node.js server is struggling with memory limits, or if it is throwing specific HTTP error codes that indicate an underlying failure in the application logic.
Since you mentioned error codes, what is the fundamental difference between 400 error codes and 500 error codes?
The difference really comes down to who is at fault for the failure. A 400-level error code represents a client-side error. It means the request sent by the client was invalid or could not be processed. For example, a 400 bad request might mean the payload was missing a required field, or a 401 means the client forgot to include their authentication token. The client essentially has to fix their request and try again. A 500-level error code indicates a server-side error. It means the client did everything right and sent a perfect invalid request, but the server failed to fulfill it because of an internal issue. This could be a server crash, an unhandled exception in the back-end code, or the server suddenly losing its connection to the database.
Evaluation note. Your problem-solving framework is incredibly strong. Moving systematically from the client side back to the server and explaining the mechanisms behind the diagnostics proves you have practical, hands-on experience. Resuming the interview. For the final stage today, let us move to a coding discussion. We will not write the code out, but verbally walk me through how you would implement a solution to merge intervals. I want to hear your logic as well as your time and space complexity.
Okay, merging intervals. The goal is to take a collection of intervals, like arrays of start and end times, and merge any that overlap into single continuous intervals. My strategy would be to use a greedy approach, but that requires the data to be ordered first. So the very first step is to sort the array of intervals based on their start times. If I have intervals like 1 to 3 and 2 to 6, sorting them ensures the one that starts earlier comes first. Once the array is sorted, I can be mathematically certain that any overlapping intervals will be sitting right next to each other in the array.
Makes sense. And
Next, I would initialize an empty result array. I would push the very first interval from the sorted list into this result array to give myself a starting point for comparison. Then I would write a loop to iterate through the remaining sorted intervals one by one.
quick question on that. How exactly are you comparing them within that loop to determine if they overlap?
Right, so inside the loop, for each current interval I am evaluating, I extract its start time and end time. I then compare its start time to the end time of the last interval that I placed in the result array. If the current interval start time is less than or equal to the previous interval's end time, it means they overlap. For example, if my previous interval ends at 3 and my current interval starts at 2, they overlap. To merge them, I do not push a new interval. Instead, I simply update the end time of the interval currently sitting in the result array to be the maximum of its own end time and the current interval's end time.
And if they do not overlap?
If they do not overlap, meaning the current start time is strictly greater than the previous end time, I would simply push the current interval into the result array as a new distinct interval.
What about the complexity for this approach?
The time complexity would be O of n log n. The iteration itself only takes O of n times, since we pass through the array exactly once. However, because we have to sort the intervals first to make the greedy approach work, the initial sorting step takes O of n log n. Since O of n log n is computationally heavier than O of n, the sorting step dominates and dictates the overall time complexity of the algorithm.
And the space complexity.
The base complexity would be O of n. In the worst-case scenario, where there are absolutely no overlapping intervals at all, we would need to store all n original intervals in our new result array, scaled linearly with the size of the input.
Evaluation note. Great job tracing the logic verbally. By the way, for anyone listening, big O complexity is simply how we measure the worst-case scenario for how long an algorithm takes to run or how much memory it uses as the input size grows. Stating this before writing any code is exactly what interviewers want to see. Stepping completely out of character now to wrap up. We hope this simulation gave you a clear picture of what to expect. Here is your next step. Listen to this again, but pause the audio immediately after I ask a question. Practice answering it yourself before the candidate does. Crucially, speak your answers out loud. Thinking of an answer in your head is entirely different from articulating it clearly under pressure. Keep practicing, keep speaking your technical logic out loud, and keep preparing for your upcoming technical interview.